So last day, if you recall, so I hope you are able to see the paper excerpt that I am showing, right?
Yes, sir.
Okay. So just a second. So last day we had looked into this part of the story where we were seeing like the situation of maximizing accuracy under fairness constraints. And there we have seen like for two different values of phi, uh, the how the um, separating line or the like division line changes and gets a rotation. Okay, so and the rotation is higher when the value of phi is smaller in order to actually balance the amount of rotation that has been given to the sensitive attribute. Okay, so this was one part of the story. The other part was where we would see like what happens when you try to maximize fairness under accuracy constraints. And this is what the authors show in this second set of results. So what you see here, again, this same line as earlier is the line that separates the positive from the negative. Okay. Now, the new lines after the constraints are imposed, okay, after the accuracy constraints are imposed, have a interesting nature. And this nature is slightly different from the other type, okay, where we were having the fairness as the constraint. When we have accuracy as the constraint, the nature of the separating line actually has changed. So do you see any interesting change? The earlier one, as we have seen, these were rotated. The dividing line got rotated. Okay, so the dividing line got rotated. What happens here? Is it just rotated? No observations. Come on, you don't have any observations from these two figures. So if I try to place these two pictures side by side, this one and this one, don't you see any difference? It's the same set of data points. No one sees any difference. So here we have seen the decision boundary or the dividing line has rotated. Here what has happened? Simple geometry. What has happened? Here also there is a rotation. Anything else? Anything else that has happened? This should have been very natural, but anyway, I give you the answer. So basically, in both cases, as we see, the decision boundary has been shifted and rotated. Okay, so the decision boundary or the dividing line, it has been both shifted and also rotated. So here there was no shifting. In these two cases, there were no shifting. However, in this case, there is a shifting as well as a rotation. Now, why is this shifting? These green circles here are the z equals 0 positive. So why is this shifting? This is a hint. Why do you think that this shifting is relevant? So seeing through the data is an important acumen that you will have to learn through this course. Otherwise, it might be a bit difficult for you guys to tackle questions even in your short exams that we take. So, uh, so if you recall, what we said is that we used that fine-grained accuracy constraints to stop reverse discrimination. So basically, we did not want those that are from the zero class and those that are positive. Zero class means those that have a zero sensitive attribute, which means they are unprotected, and they are from the positive class. We did not want them to be pushed into the negative class. Okay, so that was the reason why we imposed this fine-grained accuracy constraint, so that we could impose the constraint on individual data points rather than imposing the constraint on the entire set of data together, so that this reduces the effect of reverse discrimination and does not push all the or many of the um, sensitive, non-sensitive or unprotected class guys who are actually positive and also predicted positive to the negative class. So we did not want that. Okay. So now if this shift was not there, then this boundary would come somewhere here, and then many of these points would be misclassified, right? And therefore, this would have been something which we would not expect. And that is the reason why we actually, or why the authors actually framed this fine-grained accuracy constraint in order to get rid of this kind of reverse discrimination that could be caused. Okay, so that was all about the experiments on the synthetic data. Now, as I said, the authors also did experiments on the real data sets, and in particular they used two data sets, two real data sets. So both of these actually are well known in the literature and are kind of benchmark data sets, okay, on which the authors tried to do their experiments and show the effectiveness of their model. So the first data set is the adult income data set. And the second data set is the bank data set. Now, before we go into the experiments, let us have a brief description of each of these two data sets. Okay, so this adult income data set has around 45,000 subjects. Now, each subject is encoded by a 14-dimensional feature. Now, these features could be age, education level, etc. Okay, and there are again two classes. Okay, income above 50K USD and income below 50K USD. Okay, so these are the two different classes. So income greater than or equal to 50K USD, this is the positive class, and the income below 50K USD, this is the negative class. Now, sensitive attribute. There are two sensitive attributes in this case, gender and race. Okay, one can do experiments with any one of them or both of them. Okay, so this is the first data set, the adult income data set. The bank data set has around 41,000 subjects. Here, each subject is encoded as a 20-dimensional feature vector. Again, these features are like marital status, age, etc. There are 20 such features. Okay, and again, there are two classes. It's a binary classification problem. Okay, there are two classes which indicates whether a client has a client has subscribed to a term deposit. Client has not subscribed. Okay, so these are the two different classes, and here the sensitive attribute is age. Okay, so now with these few important like characterization of the data, we can proceed to look into the experiments that they did. Now, in both cases, the authors define the protected and the non-protected class as follows. So in the adult data, the protected class sensitive attribute, gender. Protected class, now you should be able to tell me this. What should be the protected class? If sensitive attribute is gender, let me see if there are people in the class. Okay, there are quite a few people in the class. So if gender is the sensitive attribute, what is the protected class?
Female.
Yes, female. Okay. At least I have got some answer. That's very encouraging. Okay. Then here for the bank data, as I said, the sensitive attribute is age, and the age bracket which belongs to the protected class is between 25 and 60. So now with this setup, the authors went on to carry their experiments. In all these experiments that we will see, they had a 70%, 30% split of the data. 70% training and 30% test. Okay, and this was done 5 times and the results were averaged. Okay, so that is how they went on to set up their experiments. Now let us go and look into the results that they obtained. So CLR means constrained LR. Okay, and the first result, this is how you will read the result. This is for the adult dataset and this is for the bank dataset. Okay, now the first thing that the authors are plotting are the empirical covariance and the relative loss function. Okay, so what do you see? For the time being, let us ignore SVM. SVM gave very similar results. Let us look only at the LR. What do you see? What are some of the key observations from this plot? What does this point indicate? Let us go step by step. This is zero covariance, which means what? Zero covariance means what?
Completely fair.
Fully fair. And at this point, relative loss. Relative loss means the loss difference between the unconstrained loss and the constraint loss by the unconstrained loss. So the relative loss is at this point is maximum, right? Now, as the covariance decreases, what happens? As the covariance decreases,
Loss is also decreasing.
yes. And finally, sorry, the covariance increases. I'm sorry. As the covariance increases, this is the increase of covariance. Okay. Here the covariance is 0 at this point. This is the increase scale of covariance. This is ulta. Check this. This is plotted in a, so the x-axis is inverted. See it? So as the covariance is increasing, the loss becomes 0. That is the difference between the two losses, the constrained and the unconstrained, becomes close to 0 as the covariance increases. Makes sense, right? So here it is fully fair, where covariance is 0, loss is maximum. I mean, the relative loss is maximum, and then one increases the covariance. Okay. And as the covariance increases, it goes further away from the fair classifier. Okay, it becomes more and more unfair, and it slowly converges to the unconstrained classifier. At this point, the relative loss becomes 0. Okay, same is the case for the other one, the bank data. Now the next one, P% rule versus the empirical covariance. What do you see here? Again, the covariance is plotted ulta. So what is this showing? So what is your guess? At what point roughly is the covariance 0? At what point of the P%?
The
What is
highest P% value will have.
highest? Highest to 100 hai.
Highest for that particular plot, I think so.
Highest for that part. I mean, look only at the like magenta colored plots, only the CLR. Okay. Now it starts from here. So this is the point where your empirical covariance is 0, and this kind of matches with the P% rule at a point somewhere a little higher than 75. So what is your guess? What would be that point roughly?
Like
Any thoughts?
76 or something. I don't know.
77 or 78?
70.
Something like that. Or maybe, okay, let's go a little bit lower, 77 to agree with you. So remember we said that 80% rule. 80% rule is a good number. Okay, for like adhering to disparate impact. This is what is being or getting shown here. Do you see that? Same is the case for the bank data. Bank data actually it is, I mean, slightly more like revealing. Here it's almost close to 80%, I would say. In fact, maybe a little larger than that. Maybe 85 or something. Oops, what is happening? So we said, right, the ratio of the two classes should be like maintained at 80%. Okay, that is what is coming out here very nicely. So the models that the authors build, actually, if you keep the value of C close to 0, then you are kind of able to ensure something like close to 80% disparate impact rule. Okay, so this actually further establishes the efficacy of the models developed by the authors. And here, the last one, this is kind of understandable from the results. So you have the P% rule on one side and you have the accuracy. So if the P% rule is increasing, the accuracy has to decrease, right? So P% rule means more fairness, more accuracy. Okay, and at some point you will have to say, for instance, at 80% you have roughly around 80 8.835 or 836 kind of accuracy, which is like not much compromise from the overall accuracy. Okay, similarly here for the bank data. So again, This is the fairness axis and the accuracy axis. For fairness, and of course, like at kind of 80%, you are able to maintain something like, so note that this is between 0.9 and 0.91. It should be somewhere around 0.906 or something, I guess. So you are able to maintain a decent accuracy, like with a good gain in the fairness value, if you wish to keep like the 80% rule. Okay, so that kind of proves the efficacy of the models developed by the authors in removing the uh, unfair consequences of unconstrained classifiers. So that was like when they were trying to maximize accuracy under fairness constraints. Now the same thing they also tried to do on the other side, as we said, like we have the other part also where they had the accuracy constraints and they were maximizing fairness. In this case, if you remember, there was this gamma parameter, okay, the multiplicative gamma parameter. Now they are showing two types of results. One is the fine grained gamma and the other is the normal gamma. So basically this is the aggregate one, the aggregate result, and this is the fine grained result. Okay, so in all cases, what you see that there is a nice handshake of the accuracy and the multiplicative loss factor, okay, at which you can desire a good amount of, say, p% rule. Okay, so for instance, if you take this intersection, this actually coincides with, so here the gamma would be somewhere around, okay, this is a log scale. So the gamma is like 1, 2, 3, 4, 5. So at gamma equals 5, you are already able to achieve 80% rule, and the accuracy is kind of 0.81, I would guess. Okay, so this is a good enough accuracy compared to the maximum achievable accuracy. Okay, and like you have a 80% rule already adhered to, like for a value of gamma. So you're able to find a gamma for which this actually happens. Now the same thing here, like uh, this would be a little larger than 10. Uh, Not sure, something like 18 or something maybe. So and this is 70%, okay, and an accuracy of 80%. You can in fact go a little higher up also and choose a gamma like close to 20, which will probably hurt the uh, accuracy a bit, but will ensure a little bit of higher p% rule. Okay, so the choice depends on the design engineer. So finally, once you have this plot in front of you, the choice is on the design engineer. Okay, so this was all about, roughly all about this particular paper. I think we have spent a good amount of time discussing this paper. So today, for the rest of the time, we will start the next topic, but we will just introduce ourselves. Right? We will not go into the details of the things. We will just introduce ourselves to the idea, uh, because I thought that might be a bit of a interesting stuff uh, to like to dedicate some time to, and therefore uh, we can have this discussion, and then from the next week's class we will take up in details this next topic, like with all its mathematical formulations, etc. So as I said, in the FairML part, we had all these like disparate treatment, disparate impact, etc., etc. And we saw like how to, we got some idea about, how to um, get rid of some of these inadvertent consequences. Like if you leave the machine learning classifier unconstrained, and we know now that how in a principled manner we can place in constraints which allows you to get rid of all the discrimination, or at least partially all the discrimination that are, or at least a subset of the discrimination that are known in the literature. For instance, we have seen how to avoid disparate treatment. We have seen in very elaborate details how to avoid disparate impact. Okay, so now in the second part of this topic, we will talk a little bit about embeddings, and in particular word embeddings. So anyone knows what is a word embedding? Can anyone give a small briefing?
Sir, mapping of a word in natural language to a vector space.
Very good. This is Hardik, right? I'm hearing the voice after a long time.
Yes, sir.
Yeah. Okay. So basically, here the idea is to map a word, let's say W, into a vector space. Okay. The corresponding representation of the word in the vector space is denoted by the vector of W, and this belongs to a d-dimensional real space. Okay, so this is how the embedding of a word is in general represented. Now, question is, why do we care? Why do we care about this kind of embeddings? Any reason? somehow these vectors encode the meaning of the word for computer programs to interpret. This is one thing. And the other thing is they come very handy in identifying semantic similarity between words. Okay. So these are some of the basic like uh, like basic requirements of the word embeddings, or this is the reason, these are some of the reasons why one cares, or one as a computer scientist cares about building such word embeddings, or sometimes also called word representations. Okay, so uh, now one very interesting like variant of this semantic similarity is the analogy puzzle. What is an analogy puzzle? The analogy puzzle is something like this. So you ask your computer, man is to king as woman is to X. And the computer is tasked to actually solve this analogy and get a suitable answer for X. Okay. More formally, one can write it as man to king, then woman to X. Okay. Now, can you tell me how this problem can be solved if we have the vector representations of words? How does word vectors help us in solving the above analogy?
We can do king minus man plus
Very
woman
good.
and dot product with all the vectors and take the one with highest similarity.
Very good. Yeah. So basically, man minus woman, you are telling something very similar to this, should be equal to king minus what? And this you can use the embeddings of all candidate words to be a place holder for X. Okay. Now, once you have done this, you will be able to find out where this difference actually is exactly or almost approximately equal. And in this case, the result that you will get is similarly, like this is not only related to uh, like pathological examples, but this generalizes. The good part of it is that it generalizes on the entire set of words or the entire vocabulary on which the word embeddings are built. For instance, if you have Paris is to France, Tokyo is to question mark. So in fact, these type of analogies are also easily solvable using the same type of argument that we have put in the above case of man, woman, and king, queen. Okay, and here the result will be Japan. Now, why are these important? Solving these analogies important. These are important because lot of NLP applications are dependent on solving such analogies. Okay. Now, this could help in document ranking, sentiment analysis, question answering. Okay. So, in all these types of tasks, downstream NLP application tasks, these kind of like embedding properties are very, very handy. And therefore, uh, computer scientists have like developed a very keen interest on studying the mathematical representations of words and what uh, like what interesting problems uh, can be solved by like having this kind of mathematical representations. Okay, and like as you will see, if you look at the NLP literature these days, like word embeddings and use of word representations like are omnipresent. Okay, almost every other NLP paper will talk about some form of word representation or other. Okay, however, there was a paper written in NeurIPS. So this is one of the very well-known conferences in AI, and especially like in the deep learning community. This paper was written in 2016, okay, by Bolukbashi et al. Okay, and where they showed that word embeddings could be highly sexist in nature. This was one of the nuances that was still not very well discovered or still not very well discussed in the literature. So this was a nuanced observation for which this paper has become very, very famous. Nuanced observation that was still not reported in the literature. Okay, and they started with a very simple motivating example. I'll show you this example and we will stop here. Again, the man minus woman. What do you think would the embedding calculations return? When they tried to solve this analogy, just like the previous analogies, what is your best guess? Basically, if man is to computer programmer, woman is to what? Okay, tell me what should be the ideal result? What should be the ideal result?
Computer programmer as well,
Computer
because both.
programmer as well. Okay, computer programmer as well. Very good. Computer programmer as well. Because this profession does not have anything as such which is like, connected to gender. It is not modified by any gender properties. So therefore, this result should be also computer programmer. Okay, ideally. But to the surprise of the authors, the result that came out was homemaker. And now you think that all these types of computations also take place in the downstream NLP applications. And therefore, a lot of biases could creep in into the decisions that those NLP models are taking based on this kind of computations. Okay, so it seems like that the embeddings embeddings are biased as far as occupation words are concerned. Okay, so these are also sometimes called gender stereotypes, which means that it is stereotyped in our brain that some professions are connected to some genders. Although those professions are completely gender neutral, the professions that are completely gender neutral, they are sometimes like, this is because of the culture, the society, and things like that, they become actually gender stereotypes. So certain genders are associated with certain types of occupations more. And this is also like featuring in the embeddings, because the embeddings are generated from data, and this data in turn comes from real life. Okay, so therefore the real life biases are actually also creeping in into the data, and this actually perfectly justifies the title of the paper that we are going to talk about in the next week's lecture, which is Man is to Computer Programmer as Woman is to Homemaker. Debiasing word embeddings. So basically, they will establish that there are biases that exist, and then they will propose algorithms to debias these biases. That is all about the paper that we are going to read next week. We'll stop here.
So there's a question.
Hmm.
So whatever we've seen up till now, they're very binary. So it's man, woman, and even in this paper that you mentioned,
Hmm.
like this concept that you're mentioning, it's man, woman, and so in case we bring in any third gender, will it still work? How, like, if we do say man minus transgender,
Hmm.
and ask for
Very good
another X
point.
there.
Very good point. Excellent point. So, uh, like, there has been very less work on non-binary genders, almost none. So, we recently published a paper in Kai case studies where we first, for the first time, we looked into non-binary clothing items and how biased the systems are, like the different style recommendation softwares are, like in the light of this non-binary clothing items. Maybe I can share that paper with you guys. You might take a little bit of interest in that. Uh, but yeah, you are very correct. Like non-binary gender is something that has been like discussed very less in the literature, and presently like one of the like prime areas of research focus for Siddharth, who is working as a PhD student with me, who is also a TA in your course, is studying like this non-binary genders and the biases that um, are specifically um, like uh, uh, like relevant for these non-binary genders.
Okay.